memorize for your external. So, getting into gravitational force and fields. So this is the syllabus requirements for gravitational force and field. You need to understand Newton's law of universal gravitation, solve problems, and define gravitational fields. So, gravity is the attractive force that two masses experience between each other. And Newton's law of universal gravitation describes quantitatively the equal gravitational forces acting between two bodies based on their mass and the distance between them. So what this tells us is that, and this equation is on your formula sheet too, what this tells us is that our force of gravity is going to be greater if the masses are greater, which makes sense. If you have, like the sun is going to have more gravity than like a paperclip. However, the force experienced by the two bodies is going to decrease as they get farther apart, which also makes sense. And then our big G here is our gravitational constant, which is a number which is written in your formula book, so you don't need to remember it. The other important thing about this slide is to remember that the forces experienced by the two masses are going to be equal. So even though this blue mass here is bigger than this green mass, the forces exerted on both of them are going to be equal. So have a quick think about why that might be. Pause the recording if you need to. But the reason that the force exerted by both bodies is going to be the same regardless of their mass is because, remember one of Newton's laws, every force has an equal and opposite force. So, or every action has an equal and opposite reaction. So what this means is that the forces exerted by the two masses are going to have the same magnitude. However, the effect is going to be different because of the law of inertia. So the force exerted by the two masses is going to be the same. However, this mass is going to kind of feel more of an effect because it's smaller, so it requires less energy to move. And this mass is going to feel less force than that. It's going to move not as much because it is larger, so it requires more energy to move. Okay. So now getting onto gravitational field strength. So we've seen that gravitational fields exert a force on masses within them, and that the force is dependent on the object's mass. We can define the gravitational field strength, G, as the amount of gravitational force per unit mass. So on Earth, our G is 9.8 newtons per kilogram. However, of course, the gravitational field strength is going to be different at different areas. So the gravitational field strength, as you might know, on the moon is a lot less because the moon is a lot smaller, so it has a lot less gravity. This is the formula that you will need to use to determine the gravitational field strength. And the force on an object, given the gravitational field strength, is going to therefore be equal to G multiplied by the two masses divided by R squared. So this tells us the strength of the gravitational field, the 9.8 meters per second squared. That's the acceleration, the 9.8 newtons per kilogram. And this one tells us the force that an object is going to experience as a result of that gravitational field strength. So of course, the force is going to be in newtons. So, getting onto orbits. So for orbits, you need to recall Kepler's laws of planetary motion. You need to solve problems involving Kepler's third law, and you need to recall that Kepler's third law can be derived from the relationship between Newton's law of universal gravitation and uniform circular motion. So, for recalling Kepler's laws, what I'd recommend is again going to the QCEE official definitions and memorizing those, just so you don't get mixed up with anything. So, as we can see here, when we're talking about orbits, gravity is always going to be directed inwards towards the mass body, because remember we are talking about circular motion in a sense, or the orbital motion. If an object is moving perpendicular to this force at a velocity equal to the velocity the curved surface of the planet moves away from it, then the mass will fall away from it at the exact same rate as it falls towards it. So, what this tells us is that gravity acts constantly to change the velocity direction of the satellite. Okay, so moving on to the law of ellipses, and this is one of Kepler's laws. So the law is that all planets move in an elliptical orbit around the Sun, with the Sun as one of the foci. So, all of these maths down here, you don't need to know, but it is good to understand. Remember, an ellipsis is a kind of like an oval shape. And there are going to be two foci, one here and one here. So, as you can see, the Sun is going to be one of the foci, and the planet is going to move in an orbit around with the Sun as one of the foci. The law of equal areas tells us that in any given equal time periods, the area of the ellipsis that the planet orbits covers will be the same. So, what this tells us is that if these two shaded areas are equal, because there is like a greater distance to cover here than over here, there's a greater distance to cover here, but this has to be done in the same amount of time as Q to P. So the planet needs to move faster when it's closer to the focal point and move slower when it's further away. Okay, and this is because as a satellite moves towards the body that it's orbiting, the gravitational field strength and thus force acting on it increase. And as such, its velocity increases because there's more force acting on it. Okay. The law of harmonies. And this is just the third law, and as you can see, it is the the equation that you are given in your formula sheet. And it tells us that the square of the period of any planet's orbit is proportional to the cube of the semi-major axis to its orbit. So you don't actually need to remember the definition in words because this formula is given to you in the formula sheet. So the T is the period in years or seconds. G is the gravitational constant. M is the essential mass, the mass around which the satellite is orbiting. And A is going to be the distance semi-major axis. Or in other words, the radius. So, we don't need